Here's a brief introduction to energy and work. So we'll call this part 1. And you can find this on Moodle, guys. Okay. Well, so far we've gone into kinematics and we've dealt with Newton's laws of motion. But a really powerful method of solving problems relies on the concepts of work and energy. So let's go through a few definitions here. Okay, well, the middle school definition of energy is the ability to do work. Okay? And the flip side of that would be that work is the transfer of mechanical energy. Now that's mechanical energy. Okay, work is the transfer of that mechanical energy. If it was non-mechanical energy, the term would be heat. So maybe I could put that here. Heat, on the other hand, is a transfer of non-mechanical energy, called thermal energy, right? In this case. So it's a transfer of thermal energy. Work is a transfer of mechanical energy. Alright, so energy is the ability to do work. Work is a transfer of mechanical energy, whereas the non-mechanical version would be heat. Heat is to work as thermal energy is to mechanical energy. Okay, now there are two basic forms that energy can take. One is kinetic energy. Kinetic energy. And a lot of times you'll see it written as KE, but on the AP tests they will just simply use capital K. So you need to be able to deal with both of those symbols. Now, just like in chemistry, the international unit of energy is the joule. So I should put that up here. The unit that we're going to be using, the unit of energy, is the joule. And that's symbolized by a capital J. Okay? Alright. Well, kinetic energy, the formula for it is 1/2 times the mass times the velocity squared. So kinetic energy, or KE, is equal to 1/2 mv squared. That's a keeper. There's a good formula right there. And of course, just like all forms of energy, kinetic energy is written in units called the joule. Okay? So let's take an example. Let's say that we have a ball and it has a mass of 5 kilograms. Okay? And it's going at a velocity of 10 meters per second in this direction here. And we want to know what its kinetic energy is. So we just simply go ahead and substitute our values in. 1/2 of 5, and then we have 10 times 10 squared. So that's 1/2 of 500, or 250 joules. Easy enough. Okay. So notice the kinetic energy changes with the square of the velocity, and that's important. Keep that in mind. Okay. If you double the velocity, what happens to the kinetic energy? Well, just try putting a 2 in here. So 1/2 m times 2 squared. What happens if this is just constant here? The only thing changing is velocity. What if we double it to 4? So go from 2 to 4. What happens to the kinetic energy? Okay, so every time you double the kinetic energy, the velocity, the kinetic energy goes up 4 times. What if you triple it? Okay, what if instead of going from a velocity of 1, we go to 2? That means we've increased the kinetic energy 4 times. What if we go now and triple it compared to our velocity of 1 unit? Well, then it becomes 9 times bigger, doesn't it? So the kinetic energy goes up as the square of the velocity. The other form that energy can take, the other mechanical form, would be gravitational potential energy. Okay, so I'll just put potential energy here. Now there are other types of potential energy besides gravitational. So I'll just write gravitational here for now. And later on we'll get into elastic potential energy. So gravitational potential energy I can just put as GPE here, or I can write it as capital U like they do, and I'll just put a little G here, which stands for gravity. Okay, so gravitational potential energy is equal to the object's mass times the acceleration due to gravity, the gravity field G, which on Earth would be 9.8 meters per second squared, times the height, just the vertical height. Okay, so if we want to take an example of that, let's take our 5 kilogram mass again, just as an example, and we'll move it from a position here on the ground up to a position, let's say here, and we don't have to go straight up, we can just move over here, which might be, let's say, a distance of 20 meters above the ground. So the height is 20 meters straight up. How much gravitational potential energy does that object have at this position? Well, we just go ahead and substitute in. So the mass is 5 kilograms, gravity is 9.8 meters per second squared, and the height is 20 meters. So we go ahead, 5 times 20 is 100, times 9.8, that gives us 980 joules. So the gravitational potential energy of this 5 kilogram mass, if we move it up to a height of 20 meters above our baseline here, that's equal to 980 joules. So in summary then, we have kinetic energy, K, is equal to 1/2 mv squared, and if we double the speed, that quadruples the kinetic energy. If we triple the speed, that makes our kinetic energy 9 times. If we make the velocity 4 times bigger than it originally was, we get a kinetic energy 16 times bigger. That squared value makes a big difference there. The formula for gravitational potential energy is mgh, mass times gravity times height. And all we have to do is multiply the 3 together. We'll get how many joules of gravitational potential energy that object has due to its new position. Okay. Now let's look at the definition of work. We know that work, according to what I said before, is the transfer of mechanical energy. But as usual in physics, there's a formula that goes along with it. Okay, so let's look at work now. Work is also in terms of energy units. Okay, so we would express work in terms of joules. Okay, so again, just to reiterate, it's the transfer of mechanical energy. Okay? Here's the formula that goes along with it. Work is equal to a force times the distance it moves, but it has to be in the same direction as a particular component of that force. So force times distance. Work equals force times distance, but the distance needs to be parallel with the component of force. This dot here is just not any old multiplication symbol. This represents a dot product. It's called a dot product. And the dot product basically says that this, in this case force, dot distance, that's equal to the magnitude of the force vector times the magnitude of the displacement vector times the cosine of the angle between the two vectors. Okay? So work is a dot product, and a dot product simply means that you take the magnitudes of these two vectors, multiply them together, and then multiply them by the cosine of the angle between. So let's say that you were pulling some crate across the ice, let's say. Let's ignore friction for now. And you're pulling up at this angle with a force of 100 newtons. So F would be equal to 100 newtons, but that's not parallel with the direction that the crate is moving. The crate is moving this way, let's say 10 meters. So delta X would be 10 meters parallel with the floor like this. But you're pulling upward because your height is bigger, so you're holding on right there. There's your shoulder, there's your head, and you're pulling like this, trying to move it to the right. Okay, let's say this angle here is 30 degrees. Okay, well, how much work would be done? What is the work done in moving it from here to 10 meters forward over there? We can't just multiply 100 times 10 because they're not in the same direction. So what we have to do is take this mass here and imagine that we have a component of the force vector parallel with that floor. Okay? We'll look at the components of that force vector. The component here is 100 cosine 30. So that's where that cosine comes from. That allows us to deal with the component of the force vector that is parallel with the displacement. So now we can go ahead and plug our values in. So this cosine goes along handily with the force. F cosine theta is really just the component of the force vector that's parallel with the movement. So now I'll just go ahead and plug in. Force is 100 newtons. The displacement is 10 meters. And cosine of 30 degrees is 0.866. So we have 1,000 times 0.866. So that's equal to 866. And look at the units, Newton meters of work. Well, it turns out that 1 Newton meter, that's the definition of a joule. So the work then is equal to 866 joules. And remember, work is a transfer of mechanical energy. We've transferred, we've used energy to move that crate from here to here. Has there been a change in potential energy? No. Has there been a change in kinetic energy? Yes. It's gone from a velocity of 0 with kinetic energy of 0 here to some kinetic energy of motion as it was moving. Thanks a lot, guys.